Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Shafinas binti Salmi and I'm the first presenter from Gubeta. I will start present about our project on constant strain triangle analysis CST. We start with the introductions. A tin plate have a wide applications in civil, mechanical, aeronautical and marine engineering design field. They are also extensively used in modern engineering as structural elements such as aircraft, ships, and industrial structures. In our study, we are required to do finite element analysis on a tin plate, and as the tin plate given is vertically and horizontally symmetry, we use mirror symmetry approach to simplify the analyzing method. We first use the ANSYS software to do the finite element analysis, where not only the result obtained for each node, the result also cover the whole surface of the tin plate. And next, we did the analysis using the Octave programming software, where in the end, the result from both methods using ANSYS software and programming Octave software will be compared in the end of the study. The CST elements used is a notch tin plate with given R over D and W over D ratio using 6 nodes in each elements, and the symmetry applied in this analysis always expedites modeling of a problems. Next, we could also obtain the optimum number of CST elements in the end of the study. We move to the objectives of the study. First, we aim to study the finite element analysis on a notch tin plate with appropriate boundary conditions using CST elements, where we will compare the outcomes of the analysis using ANSYS software and Octave software. Next is to determine the optimum number of CST element for finite element analysis, where we would do multiple ANSYS software analysis and get the optimum number of elements for the CST after getting a converging result. We move to the program modeling and start with the formula. The first formula involved in this analysis is displacement function U in terms of nodal displacement Q using the shape function N. Next, when we derive the strain function of the analysis, we could obtain the strain displacement matrix P. Then we derive the stress equation to obtain the material matrix form D. And using those equations, we could obtain stiffness matrix elements equation. Using the work potential equation, we can get the traction force for the tin plate analysis. We move with the modeling of a quarter model. The thickness given for the tin plate is 5 mm, and the analysis is done according to the diagram shown. And the plane condition is a plane stress, where deformation occurs in plate used in the study because model is thin compared to its entire area. And the boundary condition and load for the model, as the plate is under axial tension load, hence they are rolling added at A and B, point load at C, and a fixed support applied at point D. Next, we move to the next presenter.
Assalamualaikum, my name is Muhammad Ikram Biamo. Today I will present about finite element analysis. In this project, we use two software, type of software which is ANSYS and software. The benefit of using Octave is Octave has C++ and Photon as its basic language, make it a lot faster. The syntax is very close to mathematical expression suitable for engineers, high-level plot command, 2D, 3D, and data visualization, and support counterplot. For the benefit of ANSYS is its capability to apply the technology at level that is appropriate for the size for the problem, execute full range computing resource, ergonomic and user-friendly. So, by using ANSYS software, we use the model generation, which is the element type. We use static structural, uh, mathematic material properties, the elastic modulus. We use 207 gigapascal and Poisson ratio equal to 0.3. For the dimension, R over D, we use 0.2, W over D equal to 1.2. So, the meshing, we create the mesh to generate the surface body. Setup, analysis type, we use all triangle method. And point load, 100 Newton acting upward in negative x direction at the left corner of the quarter model. Since it's symmetry, so we divide it by 4, then we apply 100 load. So in this solution, we will able to find x and y displacement, and also we will find the normal stress and normal strain value. And next is finite element analysis by using Octave software. So in Octave software, we required the nodal coordinate from the ANSYS software. We record nodal coordinate and the element, number of element. So it's easy for us to create the setup. So in Octave software, the boundary condition, we must apply that roller must be applied at the side edge and the bottom edge of the quarter model. Value of x displacement of node 1, 3, and 4 are 0. Value of y displacement 3, 5, 6, and 7 also 0. And there is a point load of 100 Newton is being applied to the right direction of the x-axis. For the coding flow, first of all, we need to define all the input data that we required from the ANSYS software. We need nodal coordinate, number of element, and all the boundary condition. So then we form the elasticity metric for the plane stress problem, and we use function to assemble the global stiffness metric, and then we will get the output data, which is we must compare the x and y displacement at point A and B and C between Octave and ANSYS. So next is the comparison between ANSYS and Octave result. So in ANSYS at point A, there is 2 points, x and y directional deformation. At point A, x directional deformation is equal to 0. Point B, 8.8564 times 10 to the power of negative 6. And at point C, 3.4403 times 10 to the power negative 4. And in ANSYS at y directional deformation, negative 3.364 times 10 to the power negative 5. While at point B, y directional deformation equal to negative 3.8847 times to the power 10 negative 5. And C, there is no change, which is equal to 0. The value in Octave, x and y directional deformation at point A is 0 and negative 3.5395 times 10 to the power negative 5. And point B, at x directional deformation, we will get the value 8.8373 times 10 to the power negative 6. Y directional deformation, we get negative 3.887 times to the power negative 5. Then at point C, for the x directional deformation, we get 3.4533 times 10 to the power negative 4. And y directional deformation equal to 0. So the difference between SEMM and octave, actually it's quite small. We can see at point A, there is no difference at directional deformation, while there is slightly different at Y directional deformation, which is at the value 3.1 times 10 to the power negative 8. And at point B, the difference is 1.91 times 10 to the power negative 8 at point A, and at point Y, 2.8 times 10 to the power negative 8. While at point C, we require the difference X and Y is equal to negative 1.2 times to the power negative 6, and Y directional deformation, there is no change. So we can see that the difference is very small, which is we can assume that the data we require is good. That's all for me. Thank you.
Hi, I'm Nashujia. To determine optimal number of elements, we can use convergence test. Based on the graph, we found that the displacement at point B in x direction increased as the number of elements increased. The optimal number of elements can be said is 533, as the value of x directional displacement increase and start to converge at that value approximately. After that, we compare the displacement, stress and strain in both x and y direction for both cases, which is 15 elements and 523 elements are used. We found that the displacement, stress and strain at point A, B, and C are different when we're using different number of elements. This is because the entire geometry of model will have a slight change when we increase the number of elements. So the optimal number of elements is the best option for us to determine the most accurate result. Besides, we also can compare the both cases from the error calculated by calculating the difference of value for both cases. And we found that the error between both cases are relatively small. Next, we can determine Poisson ratio using the formula of taking longitudinal strength divided by transverse strength. We're taking the normal strength at point B where optimal number of elements are used. As I said before, optimal number of elements will give us the most accurate result, and we get the Poisson ratio is equal to 0.2806. In this project, theoretical Poisson ratio given is 0.3. Hence, the percentage error is 6.47%, which is relatively small error. Besides, we also can determine stress concentration factor KT using the formula given sigma max over sigma naught, where sigma max can be obtained directly from analysis results. Sigma naught we need to calculate manually using the formula F over dt. F is the force applied, d is the dimension of flat d, t is the thickness of it. Since the project given directly the R per D and W per D both 2 ratio, so we can obtain the theoretical KT from the graph, which is 1.7. In this analysis, we assume the plate is exerted axial force of 100 Newton. Noted that the 100 Newton is applied on a quarter plate. So for a full model, we need to times 2, become 200 Newton. And the dt is the value we assume. And we get the sigma naught equal to 0.4 megapascal. One of the observations we have is the maximum stress always occurs at point C. For 50 elements used, we obtain that the sigma max is equal to 0.65715 megapascal. For 523 elements are used, we found that sigma max equal to 4.810x0 megapascal. After that, we calculate the KT for both cases using the formula sigma max over sigma naught. And we obtain that the KT for 15 elements is 1.64. The percentage error is 3.53, relatively small. For 523 elements, we obtain the KT is 12.03, and the percentage error is quite big, over 100. This is maybe caused by inappropriate assumption we made in the previous analysis. In conclusion, the objective of this case study is successfully achieved. By using the same structure, boundary condition, and loading, The deformation and stress can be obtained manually by using finite element method with the assist of Octave programming software. The other deformation and stress analysis can be also carried out using ANSYS software. Besides, ANSYS software can help us to do a simulation so we can know the condition of the model clearly. The comparison of both methods come up with similar outcomes and give minimal deviation percentage. The optimal number of elements in this study is 523 elements. It is obtained by multiple analysis in ANSYS software and by using the method we call convergent test. That's all for my presentation. Thank you for your attention.